Thank you all for joining me. This is How to Get Started with AI, Moving Beyond ChatGPT. If that's not the talk that you thought you were attending, now might be a good time to excuse yourself and get to that theater. I'm Jordan. I'm the AI strategist for SEP. We're a medium-sized software product consultancy out of Indiana, and I've been working in AI, depending on how you want to count, almost 30 years now. I started cutting my teeth by automating MUDs, and if that doesn't mean anything to you, well, talk to me later. Before we get too far into it, just a couple of, oh no, that is not what I wanted you to do. Yeah, situation is normal. And I shouldn't turn my head that quickly, otherwise I'm going to keep bashing the mic against my earrings. Anyway, what I was saying was, if you want to ask questions during the talk, I'd really appreciate it. For those of you that don't happen to be in the theater in front of me, if you could reach out via Discord in the channel for the talk. One of the proctors here will inform me when some questions come in. I'd prefer to take those during the talk. If you're in here, I'd like you to ask as well via Discord. It's kind of hard for me to see all because of the bright lights that are up there in the projection. Before we get too far into the talk, I want to start with gathering a little data. So, how many of you, by show of applause, how many of you are using AI at work today? That's quite a few. How many of you are more excited about the use of AI in your work today than you were, say, 5 years ago? Right? And that's a lot of us. Well, I wonder what it is that made it more exciting. And I'll posit that it's very specifically large language models like ChatGPT and Perplexity and so on. There are a whole heap of them, and really there was this big explosion around 2019 or so when someone wrote, "Attention is all you need." And there was a big shift in generative AI techniques around that point. But we aren't just excited because there's a big hype wave going on. There's really something underneath the hood there. And I want to share how I understand what's changed. So when I think about really any software product or any feature in a software product, I think about it in terms of these two axes. Utility is how good the thing is at what it does, how desirable it is. Whatever it is you're trying to accomplish, is it the goodness of that? And then investment is the resources that you care about and are constrained in your situation. It could be developer hours, it could be hardware costs, it could be social capital to get the thing pushed out the door, right? But the thing you have to spend and the limiting resource. Most features have some sort of shape of curve in here, and I think a lot of AI features take the following sigmoid or S-curve shape. There's this early investment phase where you're not getting a lot done. You're really just setting up how the ingestion pipeline, getting the data to the technique so that it can be manipulated with AI. And then once you've got your ingestion pipeline set up, then you really start to see things ramp up, right? You're starting to apply the open source tools or the very early algorithms against the data, and you see this big jump, bang, in terms of getting something turning over and starting to see value come out of it. And then eventually you enter this long tail phase where you've done all of the light lifts, all of the low-hanging fruit, you gathered that. And now you have to, now you have to employ advanced techniques and sort of the 201, 301 level thoughts to get that product over the finish line, get the last little bit of polish on it. If you've heard of the Pareto principle, this is effectively what's at work here. For any particular product or feature, there's this thin red line where it's good enough, right? We'd all love to take our products completely polished across the finish line, pristine, and just beautiful code and all of that stuff, but fundamentally, there aren't enough hours in the day. There's just always more work on a product or on a project than there are hours to accomplish that thing. And so you have to have a good notion of when good enough is good enough so that you can cut and start moving to the next thing. I argue that LLMs are so exciting because they really foreshorten this curve. How many of you speak, right? All of us. How many of us write documentation or send emails or write code or capture our thoughts in natural language in some way? Again, all of us. The users are used to using natural language to communicate with other people to get things done, right? That's how business works. Well, LLMs really rip off the front half of the curve. There's just no ingestion pipeline anymore. It's a text box, or it's an image file being uploaded against an endpoint or something like that. And that's really, really exciting because it means that we can get to value faster. And the other nice thing about LLMs is because they've been productized so rapidly, there's not a lot of expertise that's required to employ them. Like, if you're going to do something like RAG or a more advanced technique, yeah, you're going to have to do some reading. And you're going to have to understand how to, slice the data apart, feed the data in, and orchestrate things. But fundamentally, you're not going to have to learn, advanced or calculus-based statistics and so on to deploy these techniques on your own, because there are products that will do that for you that you can use today. And man, I've talked about it in terms of text, but man, do they do a lot of things, right? You can use them to build chatbots. They're great at converting one type of input to another type of input. You can go text to structured like JSON or a YAML or something like that. You can go text to video or an image. You can go an image to text. All sorts of transformations. They're pretty good at doing certain types of programming at the very least, especially things like SQL and structured queries. Conversational interfaces are another thing that they go gangbusters on. Question answering, document retrieval, lots and lots of use cases that are extremely helpful in producing a thing, right? They slice, they dice, they julienne fries. And if the Vegematic doesn't resonate, maybe the slap chop is a little more familiar. But it's a product, right? It's an appliance that can do tons of things and things that you might find tedious, and it's extremely useful off the shelf. But remember, the title of the talk was, how am I going to move beyond ChatGPT? And you might be wondering, if you've used these things, why would I do that? They're extremely useful. Well, they are, but the reason you might have to move beyond them is this plateau that exists out to the right in the investment and utility curve that I've drawn here. So there's a secret third axis on this plot that doesn't get talked about a lot, and it's how much knowledge you need to invest in a product. The further you move out on that investment curve, the more you have to know, or the more you have to have on hand in order to do the future investment. You have to understand the fundamental mathematics behind the algorithms to fine-tune them effectively. If you're going to build a foundational model, if you're going to build a foundational model, you need hardware that's expensive and difficult to come by. I don't have a supercomputer in my backyard or in my basement, right? I have a commodity desktop, maybe a rack or two, but building foundational models requires a data center the size of a building in some cases. I just don't have access to it. And so, if you are in one of these positions where you need a lot of polish, a lot of high fidelity results, it may be sort of out of scope or out of your budget in order to carry the thing across the line to final completion. So while they foreshorten the left half of the curve, because of this moat that's built in terms of knowledge and in terms of hardware access for fundamental models, they sort of elongate the plateau on the right side, and that can be detrimental. So there are a couple of reasons, or there are a couple of situations where you might find yourself in that right half of the curve. The first is sort of fundamental in how constrained the problem you're trying to solve is. Imagine the big gray circle is all legal token sequences that an LLM can emit. It's sort of the legal utterances that the system can give out. And for whatever your problem is, there's a set of interesting utterances, things that are meaningful to your problem, might move the needle for you. And then there are a set of things, another set of things, which are feasible. You can do something with them. Maybe they are syntactically correct and compilable in a programming setting or something like that. And what you're interested in is the size of that overlap, that intersection. If the size of that intersection is huge, LLMs are going to be a great fit. If the size of the intersection is very, very small, LLMs might not be a good fit. And if testing whether or not you find yourself in that intersection is expensive, that can also be a problem. For a more concrete example, let's imagine materials science for a moment. There are a lot of chemical compounds in the world, and we can describe, if you've struggled through organic chemistry and other chemistry courses, what compounds can feasibly be built in a laboratory? And for any given material science problem, we have certain properties in mind we'd like the material to have. So those are the useful materials, those with the right properties. And then there are those materials that are stable outside of a laboratory setting. You can make all sorts of things, but they may only exist for fractions of a second before they crumble into composite parts because they're just not stable bonds. So in that setting, what you really care about is the intersection of things with the right properties that can exist at room temperature outside of the lab. And that may be a small space, and it's not really cheap to test that. It either requires very, very expensive simulation or physical testing, which is limited by all sorts of things like human time and having the right resources and facilities in place to construct the materials in the first place. Another situation that you might find yourself in where LLMs could be difficult to employ is where human life and limb is on the line. So LLMs, by their very nature, hallucinate, right? They generate a feasible response to the prompt, and they'll always generate a response. Sometimes that response is, I don't know, but they'll always generate something. In some situations, generating something when you're not sure that it's good can be really, really detrimental. These are situations where a person may live or die based on the outcome of the decision, or where errors are just impossible to recover from. Imagine that we were using LLMs on Discovery for a second, or a rover for a second. If we issue a set of rotor motions that put the robot in an unrecoverable position, it's not like we can send someone out to Mars and just have them write the thing. It's a big, big problem. It's a very, very expensive platform, and any correction to an error is prohibitively expensive. So if you find yourself in one of these situations, LLMs may not be a good fit from the outset either. In any place where you're going to need tons and tons of polish to carry it across the finish line, where human life and limb are on the line, or where you have these tightly constrained domains, you're probably going to find yourself in a product setting moving away from LLMs. Now, I'm not saying that they're not great for prototyping, showing value, doing sort of a painted door test, things of that nature. They're always awesome for that, or almost always awesome for that. But when you talk about getting fielded products out there and the cost of failure, you may want to switch away at some point. And if you have to switch away, there are, fortunately, a variety of techniques that you can go to. So we talk about AI like it's a monolith a lot of the time, and every couple of years, AI means one specific thing. 10 years ago, if I was giving this talk, I'd have been talking about deep learning as the thing AI meant. And now we're talking about generative techniques as the thing AI means. But there are all of these other things, right? You can use natural language processing, like old school NLP, to understand what's going on in text or voice. There are prediction technologies, machine learning being sort of the thing I think people will latch onto there, that let you classify objects and predict trends over time and effectively model the world. There's vision that allows us to understand the world around us in literally a visual way, right? What's in front of me by looking. And then there are optimization techniques that let you do things like long-range planning, scheduling, and picking the best element out of a set, sort of rank ordering of things. And we're going to talk through each of these areas in turn with the rest of our time. Starting with prediction. So that's modeling reality, doing some sort of machine learning or maybe deep machine learning, pardon me, and classification. I like to think about machine learning in the context of traditional software development. In traditional software development, you have your data, your input, and then the thing that we all know, and then there's the expected output, how the program ought to behave, right? And that's the thing we all know how to produce. We know what a word processor should do. We understand how an e-commerce site ought to work. And while we couldn't all necessarily whip one up here in the theater right now, we could get there, right? Even if it's not our day job to build that specific piece of software, we understand the moving parts and how to learn them. It's relatively cheap to write the orange thing here, the program. In machine learning, that's turned on its head. I know what my data is, I've collected it in some way, and I know what the output ought to be, because it's very natural for me to say, oh yeah, that's whatever it is. But for whatever reason, it's incredibly difficult for me to describe programmatically what that output, how to get from that input to that output. A classic example is recognizing birds in an image. I know what a bird is. We all collectively know what a bird is, and we might argue about some of the weirder cases. But generally speaking, we agree on the birdness of things. And it's kind of difficult to say, okay, but from this collection of pixels, what relationship between those makes a bird? I can't write that down, but machine learning can recover it from data and a number of other things. I forgot to put that in there, so let's just skip through it. One example of a machine learning program you might find yourself working on is predictive maintenance. Say, for example, you want to know when a turbine engine on a plane is going to fail, because you'd like to make sure that it gets maintenance before it fails in the air, because that would be very bad for all the parties involved. Well, what you might do in that situation is put monitoring devices on the engine, effectively collect telemetry off of it while it's in flight, and then when it lands, take that telemetry information off of the plane and present it to an expert human analyst who would say, oh, I saw this style of vibration during takeoff, and that style of vibration coupled with this loss in thrust means that there's a bleed leak in the engine, and we're not getting enough suction. And when there's a bleed leak and not enough suction, here's the thing the maintenance personnel should do. They're informed of that. The maintenance happens, it's successful or not, and everyone's happier because the plane doesn't fall out of the sky. In practice, you can also do that with machine learning, right? In fact, this is actually describing a system that I've worked on in the past. In that particular case, we had a human analyst who had been labeling these things for 20, 30 years, and we had all of this time series data to identify whether or not a problem was likely to occur, whether the analyst would have signaled that problem was going to occur in the next little bit. We could have fielded a fully automated system, right? We could have put that out in front of the mechanics directly. But because this system is so, people's lives sort of depend on the engines not failing, and so we wanted to have a human who could carry the liability in the loop somewhere, what we did instead was triage their attention. We believe these engines will fail in the next X hours, and that's probably the duration of one flight. So please take a look at them more directly and then go about your day, right? He has the same problem that the rest of us have. There's more work to do in a given day than there are hours in the day that you're working. So we were trying to triage his attention by paying attention to the most severe engine failures up front. A little bit of shaking on the plane is fine. The engine not producing thrust is worse. So please pay attention to that kind of failure before the other ones. Now that may feel a little hand-wavy, right? Like, how am I actually going to detect a problem in a time series? Well, the first thing is to sort of think about the problem. So imagine that this represents all of our telemetry data. It's one vector over time. And there's some error that's going to happen right around now. We'd like to predict that. Well, the first thing to know is that this isn't really what time series data is. Even if you're capturing data continuously, you don't really have a continuous stream of data. We have samples. It's been sampled over time, and you have a certain vector of examples in front of you, and you want to know whether or not there's a potential error in that window somewhere. So that's more aligned with machine learning if you've done it right. Like, here's the vector, here's the label. Here's the vector, the machine learning produces the label, rather. But the real trick is to slice the windows appropriately, right? What we want to know is, using history, is there likely to be an error in that window? And we can play with those window sizes to get around things like very rare failures and whatnot. But you have to be careful. I can easily make the window too large to be useful, right? If I say, well, will there be a problem in the next 50 years? Yes, of course, in the next 50 years of operating hours, there will be a problem. That's not useful to the mechanic who has to deal with the next 30 minutes of flight time. So you want to slice those windows such that they're large enough to be big enough targets to hit, but small enough to provide predictive power in decision-making, to be leverageable for decision-making for the humans that are looking at the outputs. It's not just about classification and identifying things in time series. Sometimes you want to model the world and predict the future. I assume most of us drove here today, so imagine that you wanted to use artificial intelligence to help maintain the highways. And if your trip was anything like mine down I-70, you want to use artificial intelligence to maintain the highways. One part of such a system would necessarily be predicting how highways degrade over time. Roads degrade once they're put in, and it's sort of a matter of time before they become rubble. That's why we effectively have two seasons in the Midwest. We have winter and we have construction. And so they're out there repairing all of the damage that the water did in the winter, all spring and summer long, making it difficult to get anywhere. In our particular case, in the state of Indiana, where the client who wanted this work done was, they predict highway degradation over, or they model highways as degrading to rubble over 40 years. And they wanted to know, well, how will the highways degrade? We have some data, we have some models, we need to do planning against this, what can we do? The first thing to do is to model degradation so that we can forecast the future and understand what the plan should be. The problem is that the data that existed at rest, they've been gathering information in the state for the last 6 or 7 years on highway degradation. And you may notice that 6 or 7 years is several times smaller than 40. So how are we going to predict, how are we going to regress a degradation model when we've never seen a road decay to rubble, right? We've not seen it be outside long enough to decay to rubble. And in practice, no one actually lets their highways go all the way to dust. The people that drive on them would be very angry about that, and so they tend to get repaired before they actually crumble. Well, when you don't have enough information in machine learning, something you can turn to is the information you have yourself, right? You can do explicit modeling, and that's what we would do in this case. Highways in most of the Midwest are graded on a scale called PASER. It's not important to understand what that is exactly. The important thing is they go from 10 to 1. 10 is an absolutely pristine road, and 1 is basically gravel, but worse than gravel because it's big slabs of asphalt or concrete that are arrayed in the wrong space. You need a tank to drive over it. And roads don't get better without human intervention. They just degrade. So they go from 10 to 9 to 8, and so on all the way until they go all the way down to the bottom. But the thing is that they don't always degrade linearly. Sometimes they jump a couple of steps. So sometimes within the course of a year, a 10 could become an 8, or it could become a 7, or heaven forbid, a 3 or 4, but that's typically like there's a fundamental construction error when that kind of thing happens. So there's actually a much more complicated model of how they degrade. And while we didn't have information showing how any individual road decayed in this way, what we do have is information on how each road, year over year, decayed in this model. How often did a 10 become a 9? How often did a 10 become an 8? And so on. And that lets you generate probabilities or percentages. So then you've got sort of a Markovian model, right? Given that I am a 10, how likely am I to be a 9 next year, right? Roll the dice, walk a step, and then from a 9, roll the dice and walk a step, or from an 8, right? Until you walk all the way down this model and land on a 1. And that's a whole trajectory of how a road would decay from 10 to 1, given the data that we have at hand. Now, it's an abstraction. It makes some assumptions about the world, right? That everyone evaluates roads correctly the first time. And so a 10 really is a 10 because the human said it was. There are problems there, but it's a good representation and sufficient to plan against. And so that's what you do, is you build these big models and then you walk along them to do your samples. And it may not be a sequential model like this, right? It may not be a graphical model in whatever case you find yourself in, but I'm sure that given that you know your domain, you can construct you can effectively engineer the knowledge that you have in your head into a mathematical or programmatic model that you can leverage along with data that already exists to produce the data you ultimately need. So that's how we got to the point where we were sampling these trajectories from the simulation, and then we could just do the regression the way you normally would with machine learning. If you find yourself with one of these prediction or forecasting problems, there are a huge number of libraries out there to help you. I would start with scikit-learn. It's a relatively low, I don't want to say lower power tool, but it's sort of a low effort to install, low effort to get started with. It's not as complicated as like a deep neural network tool, for example. So it's a good place to dig in. If you need more power, if you're not getting the accuracy you want out of something like scikit-learn, then I might pick up a PyTorch or something like that for your deep neural networks and your more explicit modeling. If you find yourself trying to build things like controller for robots, then you would want a different kind of learning technique that we didn't really touch on here called reinforcement learning. There you would use a tool like Gymnasium, which was the thing OpenAI worked on before anyone knew who they were. The next island I want to talk about in the metaphor that we've selected is natural language processing. And I'm going to start with something that you're going to say, oh, you can absolutely do that with large language models. And you're right, but bear with me. So sentiment analysis is a big thing that we do with natural language, right? In this particular case, we're talking about the sentiment of a restaurant reservation. We waited 20 minutes for our table. Our party was seated. Once our party was seated, the service was prompt, and the food was delicious, right? So delectable and prompt, those are very positive words in the context of a restaurant. And past might be negative, might be nothing, so we're just going to let it be, right? We're not going to carry that. And then we're going to aggregate those sentiments together to get an overall score. Very natural thing, and if you ask ChatGPT or any other large language model to do sentiment on text, it will do a pretty good job. Where this isn't maybe the right choice is where it's much more nuanced. It's in that narrow category. Imagine instead that we're asking for sentiment on reviews of funeral homes, right? No one's happy to be there. But the service can still be good. The people can be attentive. They can make you feel good about how you were treated in the context of a funeral for one of your loved ones. But all of those utterances are going to have a lot of negative sentiment too, because it's not a good time to have to bury somebody. So in those very, very narrow areas, I might switch to a specific NLP problem so that I could discard selectively sentiment about the event itself, as opposed to sentiment about the service being provided in the context of the event. Another thing that traditional NLP methodologies do very well, and I think a little bit better than LLMs right now, is categorization. Imagine for a moment that you walk into a help desk situation. It's attached with a piece of software you're working on, and you're trying to figure out which portion of the program you should work on today to deliver value for the client or for your users. One thing you might do is you might look at the number of support tickets that are being generated against each part of the program, right? And you could use that to triage your stories and order things and whatnot, depending on what your roadmap looks like. If you're in a mature organization with a great help desk setup, there's very likely some sort of provenance between the help desk ticket and the portion of your system that it's talking about. Not every company is there, though. You might just have a bunch of text-based tickets, like an email system or something like that. In that case, what you would do is find some way of binning that text together. So you would probably want to go back to predictive for the binning, but the fodder for that would necessarily be NLP. You'd be trying to do things like extract topics from emails. This is about the login system. This is about a timesheet piece of software. There's something in the telemetry collection that's not working right. Whatever it is, you're trying to extract those topics so that you can throw them all together. And then you can look at the piles and say, well, that pile's the largest, so there's my hottest fire, let's go. Another level of fidelity down is extracting deep semantic meaning from text. So this is more of a turning unstructured data, free-form text, into structured data. And this is in the context of the turbine engine maintenance program we were talking about just a moment ago, right? Part of the input in that system were actually text logs captured by pilots and mechanics about what they experienced and what they did in response to that experience. And if you can recognize a handful of phrases, right, decreased engine flow, slight veering, engine flow decrease, there are a lot of ways of describing the same kind of problem because human language is rich and complicated. But if you can recognize a handful of nouns that are important to you and very short, like sentence fragment-like descriptions of what you're looking for, you can do deep modeling on these texts and try to extract what the problem was from the way the person was writing. The reason you would do this with NLP rather than generative is because it will fail loudly and early. If there's something about the text that doesn't parse, if there is a use case where you know it's present and you're not recovering it, you'll get a very clear signal deterministically every time. And that's useful for troubleshooting the system. And when you're trying to consume that data later on to make life and death decisions, the fidelity of that extraction is paramount. So you want the sort of noisy failure mode that the old style NLP provides. This also actually came up in the highway maintenance program that we were talking about previously. A thing you want to do in any highway maintenance program is naturally display the highways that are being maintained in their current state. The state of Indiana records, those are real data entries from one of the agencies in the state of Indiana what the roads look like. And some of them map very naturally to map data like Thayer or open road maps or whatnot, right? But some of them are awful. So Benjamin Street between a private driveway and a fire station driveway, those are not things that are captured well within US Census data or within open road maps data. But we all know what a fire station is. We have other geolocation data that we can use to extract the location of the fire department on Benjamin Street. And then we can sort of work backwards to fill in more of the map for the user rather than having them hand annotate the entries where we're like, that doesn't make any sense. So this is more of a usability thing where we're using natural language processing to get more juice out of the information that the users are collecting without them. You ever find yourself in a situation where a user or a company comes to you and they have piles and piles of data and they want to do something with it, but that data wasn't constructed for machine consumption? That's the sort of situation that this is, and that's the sort of situation where NLP like this is extremely useful. If you find yourself in an NLP situation and the LLM-based stuff isn't working for you right out of the gate, these are the libraries that I think it would behoove you to take an early look at. NLTK, the Natural Language Toolkit in Python, is very powerful. It does word sense disambiguation, part of speech tagging. It can basically produce sentence diagrams from pieces of text. It'll also split up your text at the paragraph or sentence level for you, depending on what your needs are. So it's a very, very useful tool. If you're doing sentiment analysis directly, I like Vader sentiment for that because you can describe which words not to pay attention to directly in a very natural way. And if I'm not doing sentiment analysis with LLMs, that's the sort of thing I have to do, and that's why I'm using those tools. Pardon me. Optimization is the next island I want to talk about. So this is when you're trying to do some planning, long range, like what should I do day over day, year over year, or how should I schedule people for the hospital or the factory floor today? Or you're building a recommendation engine, right? Which videos is YouTube going to recommend to me and how are they going to be ordered? Well, that's optimized. The most common example, I think, or the one that many of us have experience with that's relatively simple is video game pathfinding. In video game pathfinding, you have a character, they're in a location, and they want to go to a place. And so that's the state of the world, where they are, maybe their goal as well. And then you have actions. In this particular example, the character can move to the north or move to the east. In optimization, what you're often doing is chaining together actions to alter a state to achieve some desired outcome. And you're curious about some quality of that sequence of actions. Maybe it's length, maybe the total cost of those actions, maybe how likely they are to succeed, right? Combined probability or something like that. But it's that summation or aggregate of the sequence of actions that's being optimized for. The highway maintenance program was such an optimization problem, and that may not be obvious at first blush. However, the states are the current Paiser scores of the highway. So how bad is the road today? And our actions are that stuff that we're frustrated they're doing every spring and summer, right? Are they going to tear up the whole road and repave it? Well, they might do that, full depth reclamation it's called, for a Paiser score of 1, 2, or 3. But for a higher Paiser score like a 7 or 8, maybe they'll do some crack sealing, those black snakes you see all over everywhere that repair the water barrier and keep water from getting underneath the road and becoming frost heaves in the winter. So those are your actions, and what you're doing is you're chaining together actions on the state, and the state is both the status of the road, like I said before, and the budget that the municipality has available to them. Because unfortunately, no agency has enough money to fully maintain their roadways. No one wants to be taxed at that rate. So they have to figure out what they can do with a fixed budget. So what you're doing is, okay, well, for this road segment, here are the available options, and I'm going to take this particular treatment. That'll make that road this Paiser score in the next year, and it'll take this much out of this year's budget to do that. And you walk down these choices, right? Well, now I'm going to take a second treatment on a different road segment and a third treatment on a different road segment and so on. Eventually, you run out of budget. You just don't have any more money to do anything. At that juncture, you have a plan for the year at the very least, and that plan can be evaluated. Well, how good are my roads after a year of applying that plan? And if this looks a lot like tree enumeration, that's because that is tree enumeration. And I think if you're from a traditional CS background, this is something you've encountered at some point in your life. And if you're not, there's no magic here. It's walking a tree. It's a simple data structure. It takes a little bit of time to come to rights with if you've never seen it before, but it's like a fundamental operation. And this is one of the things where it's like, oh, this one, maybe there's not a library. Maybe this is just a thing I write directly. The other thing I want to point out here is that most of these applications of AI are leveraging multiple things under the hood, right? So the product itself that the client was selling, in this case, is highway asset management. How do I maintain the roadways for an agency as a professional service? They had this budget optimizer in their back pocket to make their professional services offering great. It wasn't quite the product being sold, but it was the software that enabled the product. And then within that piece of software, there were a couple of different AI techniques that enabled that software to work, right? We had optimization, prediction, and natural language processing. And that's what I find in most AI deployments, is that there are a couple of different techniques being leveraged for different kinds of problems that the software is encountering. And then there's a whole heap of software that has to exist outside of the AI. Otherwise, the AI is not particularly useful. The answers have to be surfaced to a human user and all sorts of other things. Another optimization problem, you find these all the time in heavy industry. Lumber is one of those. So if you've ever bought a 2x4 or a 4x4 at Home Depot, you may have come to wonder how it is that that wood came there. One of the steps in that process is called edging. So you take a living piece of wood and you put a straight line to it. And you can model that as an optimization problem. Specifically, what you're optimizing is how perfectly rectangular prismy the wood is, for want of a better word, and then what the grade of the lumber will be. How many knots are there in it? How much sapwood is present? Is there any worm-eaten pith or something like that? You want to minimize those things. But the optimization problem is fundamentally still a tree enumeration, right? So in this particular edger, you could twist the board a little bit, left and right, and you could decide where the saw blades were going to go. And this one had 3. So what you're going to do is figure out the orientation of the board as it comes down the line, and then you're going to place one blade and then a second, and that'll define a single rectangular prism. And then the third blade would describe a second one if you could extract it, if the wood was wide enough. The thing that I find really interesting here is the timescales of these two problems. So for the highway maintenance problem, they need 1 plan a year, maybe 2 plans a year in the worst case. You can literally use like 6 months of computation if you want. Now, the user may not want that. They may want a day or 2 at the outside, but still, days of computation, it's a lot of hours. Here, your decision horizon's 2 seconds. So you've got 2 seconds as the wood comes down the conveyor belt, gets scanned by the vision piece to make a decision. So it's the same AI tool, but wildly different applications, and I find that very cool. If you find yourself not wanting to write the enumeration stuff by hand, there are libraries out here for this too. There's OptiPlanner, which is a Java-based library for doing scheduling and optimization systems. And there are things like CLP, which is a linear program solver. And if that doesn't mean anything to you, it's a way of casting a problem as a series of mathematical equations and then solving those equations quickly. The final island I want to visit today is that of vision. And it is exactly what you think it is. It's what it says on the tin. So maybe you want to do something in the manufacturing space. To come back to our turbine engine example, turbine engines have discs of turbine fan blades in them. And each of those blades has tines like this. And the engine moves quickly, and sometimes bird strikes happen or other debris comes through the engine. And so those blades can be harmed. They can be ablated by those sorts of eroding processes, or they can be added to by, you ever worked in an engine? There's oil and all sorts of things, right? So there's also buildup on top of them. Part of the maintenance process is to read the serial numbers off of the blade itself. That can be difficult to do because of the erosion and the additive processes of the blade in flight. And also, it takes an expert, a human expert, time to sit there and eyeball it. And that's time that they could be using calipers on the thing to measure how damaged it is and decide whether or not it should go back on the engine, right? It's not a value-add process to do the labeling. You can use computer vision to do the labeling itself. The lumber mill project we just talked about, that also uses a bunch of computer vision, and it uses two types of computer vision, which is the thing I want to draw attention to, right? There's a traditional camera that's telling you things like the color of the wood, where the knots might be, is the sapwood, worm-eaten pith? You need the RGB image to make that decision. But then there's LiDAR, which is another type of vision that gives you a depth of the lumber. How far is it from me to each point on the board? And from that, I can effectively understand the shape of the wood. If you've ever played with one of those pin boards with your hand, that kind of a readout, right? That's a different type of vision. You could have also used thermal imaging here if you wanted to. It wasn't necessary for this particular process, but computer vision is not fundamentally limited in the same way that the human eye is, which can be very useful. And while you might imagine that in that knot detector shown on the left, I guess, you might imagine that we would do that with a predictive technology, right? We'd have some poor sod, probably me, sit down with a bunch of pictures of wood and circle all of the knots for a couple of hours so that we had a training set. We could have done it that way, but there are simpler, more algorithmic approaches in computer vision as well. In this particular case, we did line detection to find the grain of the wood, and then on that line map, we did circle detection to figure out where the circles are, because all else being equal, a knot is a circle in the grain of the wood. So you don't always have to go straight to predictive technology with computer vision. There are simpler algorithms, corner detection, edge detection, foreground and background detectors, which are not ML-based, that can be extremely helpful for particular applications. Another place that computer vision comes up a lot is in the healthcare space. So imagine that for a moment that you need physical therapy, and for whatever reason you can't get to a physical therapist. Maybe it's too challenging to get into a vehicle because you've just had hip surgery, and sitting down and getting up just isn't going to happen, right? In that case, maybe it's too prohibitively expensive to have a therapist come to you. What you might want to do is have a computer watch you go through your physical therapy exercise. It can measure what your pose is, how much your hip is deflecting and how much your spine is deflecting through your hip and so on, and say whether or not you did the rep correctly. And then say, that rep wasn't clean, you need to do it again. If you haven't had the joy of going through physical therapy, that's the bulk of it, is, no, you didn't do that right, and now you need to make yourself suffer, because otherwise you're not going to heal correctly, so do more. Whether or not you'd want that coming out of a robot is a separate sort of UX concern, but it is definitely a thing that you can measure. If you find yourself wanting to do computer vision, OpenCV is the library. OpenCV is fundamentally a C library, but there are bindings in every language imaginable. And this will do all of your algorithmic-based stuff, as well as provide you the hooks to produce a vector of input that you can use to do more advanced ML tomfoolery, if that's what you have to do to get your data out of it. So in summation, I know we talk about artificial intelligence as a monolith, but it's really not. There are a bunch of different islands, there are a bunch of different subfields of AI, and each of them provide unique tooling that we can use in various situations. Generative is the big new island that everyone's very excited about, because there's been this recent lurch forward in capability there. And it's right to be excited about it. It's super, super cool. But there are situations where generative techniques are not the right choice. If you find yourself needing just absolutely perfect polish on the technique, you may not be able to get there. If your domain is incredibly constrained, like some of those planning domains that we just saw, you may not be able to hallucinate or to generate a plan that's feasible. And if your product in some way puts people at risk, right? If its operation or failure could save or harm lives, LLMs may not be the right choice. If you're, in any event, no matter what technique you're using, if you're using AI in a software product, chances are you've got a bunch of different problems ahead of you that could be tackled with AI. And picking the right tool for the job and merging those together rather than always using a single hammer is going to give you a better outcome overall. So you should think about what tool is going to best solve a particular problem in front of you and pick it. And there are a huge number of tools, open source libraries and whatnot, available for you to get started. You don't have to write these things from scratch. It's not like we're picking up Russell and Norvig and turning to chapter 4 to look for our machine learning algorithms, right? People have done a lot of this fundamental work for you already, and that's really the right place to get started. And you should get started, because it's cool stuff. So with that, thank you all so much for your attention. I think that we've got quite a bit of time left for questions. I don't know if anything's come in from Discord, but if you folks here have anything, I think I can see you at the very least. Thank you. Yeah, sorry, I can't see you, but shout it out and I'll repeat it.
So for teams that have an LLM application that are more in the analytics space than the software development space, they tend to find, they tend to want to use ChatGPT and different models to like speed up their NLP, NLU approach because like the time to market for like the custom tooling can take them a long time. They're not skilled necessarily the same way as like software developers. So like what are your recommendations around either upskilling your analytics folks in terms of like getting to market faster with NLP, NLU type tasks, or just resources that they can leverage?
Sure. So the question was for an analytics-based team. Maybe they've already got some LLMs fielded, and they want to use those because doing these more bespoke things is a heavier lift, right? It reduces their time to market. They may not already have those capabilities in-house or readily available to them from another team, but they still need to get their work done. That's not just restricted to analytics. That's like every business function ever, right? Even from the pure engineering teams, you see people are like, I want this machine vision stuff and I want the more bespoke stuff, but I can just ask Perplexity or a foundation model to interpret an image for me, and maybe that'll be good enough and I won't have to learn the OpenCV piece. In those cases, there are a couple of things that you can do, right? So part of it is organizational. You can build a set of resources for those people to lean into to help. That's sort of our model where I'm at. Not everyone has deep AI expertise within our software development group, but we have a set of dedicated resources for AI-specific development, and we come in when those things are needed. But again, there's still a constraint problem. We're like, well, everyone wants the time, and there are only one or two of us, right? So that can be a fundamental problem. In terms of upskilling, there are a number of online courses of better and worse quality. I think really the place to start is more understanding what's available. For that, I think Rebooting AI is a fine book. I think AI for Dummies can also be very useful there. Those are both sort of very case study heavy descriptions of the possible. For actually learning the stuff itself, honestly, you can do a lot worse than the tutorials that are available online that leverage these libraries. If you can call a technology shot as the technologist in your company and then point them to this stuff, that would be a good place to start. Does that address your question? Thank you. Yeah.
I'm new to AI. I'm not done much programming yet. So the hallucination of the LLM, is it really just bad data in, bad data out, or something else?
So the question was, with LLMs, is it really sort of a bad data in, bad data out setup? Yes and no. So you see a lot of people in the large language model space talking about pre-LLM internet data as like the pre-nuclear age steel in the same kind of breath. And that's not entirely wrong, right? There's a substrate of data that was entirely curated by hand, high cost to produce, and therefore high value data. LLMs have fundamentally reduced the barrier to producing any sort of data, and that's made some of the things that are available much lower quality than they might have been previously. So you do have that problem going for you. But the other thing is that it's the fundamental nature of what the LLMs are rewarded for in the reinforcement and the training phase. They're rewarded for producing output that people find reasonable, that people find pleasing for whatever the person's version of pleasing is, right? That isn't limiting the output to things that are truthful or things that are enriching or things that are correct, right? Depending on what you care about. So there's also almost a fundamental alignment problem between the LLM and some of the applications you may care to deploy it for. So it's not exactly garbage in, garbage out. It's like you're using a straight screwdriver to drive a Phillips head. You can get it done, but it may cut the thing up a little bit. Yes?
I have one from the overflow theaters. Is there a too large LLM? The more data there is, the more accurate the output would be, but it would also require more processing power. Is there any tooling today that is available to help mitigate that?
Yeah, so there are tools that can help. Sorry, the question was, if you end up in a situation where you have an LLM that's too large to execute on your hardware, right? You're training these trillion parameter models, but you've got a commodity desktop to do the final thing in. Are there technologies that exist in that space? Yeah, there are technologies that exist to compress the LLM, the number of parameters that it's being executed on and so on, so that you can execute it on a more conservative set of hardware, and more conservative than the hardware it was trained on. Do I know what those are offhand? No, not exactly. But if you go to the Slack room with the, if you go to, not Slack, excuse me, Discord, if you go to the Discord room for this particular session, then one of the links is to the company's blogs, and one of my colleagues, Lee Harold, has written an article on that sort of thing that might be helpful to you. Okay, whoever said it, and then you. Yep.
Model.
Mm-hmm.
But the learnings and the knowledge from that, if it could be honed for that, the private data could be removed, but the kind of general model could be done. Are there any actions towards overcoming that problem or ways to get around that so that you can kind of filter out that commodity?
Yeah. So the question is, like, I'm gonna boil it way down. The question is, I really want to LLM or use one of these productized AI offerings, but governance. And so yeah, but governance, right? You want to keep your data private. You want to only have your access to it. There's a certain level at which now, like, if you believe the operators, right? They promise you that they won't train on your data, that they won't keep it at rest. If you believe those promises or not, that may change your posture with respect to data governance. You can always bring stuff on-prem. That was what we decided to do, was we bought somewhere between $20,000 and $50,000 worth of hardware and used some foundation models off of Hugging Face to roll things out internally, because we make certain promises to our clientele about their IP. And the only way we could really feel like we were being reasonable stewards of that was to do it ourselves on-prem with a new couple of racks of servers. And we went from 0 to that being available to our engineers to use for testing purposes over the space of about 4 weeks. And this is not the thing that we do as a fundamental, like, this isn't our bread and butter, right? This is a new capability we're onboarding. So, like, if you have people with cycles that understand setting up desktop servers and understand the fundamental underlying LLM things, it's a very, very feasible lift to get it on-prem if you have the capital and the engineering effort to spend. One of you asked a question.
How do you realistically keep up with the state of the art with all this AI stuff? Like, is there any way of actually being able to filter out what is practical, what is not practical? There is a new paper or new code sample that comes every other day, and it's extremely overwhelming.
So the question was, how do you keep up? How do you understand the art of the possible with the way the AI is moving? I think the tragic answer is you don't. So I've kind of thrown up my hands and given up as well. Part of my process is to maintain an incredibly skeptical posture. So I just don't believe things fundamentally, and then I have to go look myself. And the other part of that is I follow certain research scientists on Twitter, like people that I've worked with in my past life. I get digests from various things like TLDR and whatnot that I then go and read those articles about. My personal network is filled with AI people. So it's about finding like-minded folks that are going to do some of that pre-selection for you, relying on their judgment to bring you the goodest bits, and relying on the judgment of the people around you to bring you the most sort of pertinent and business relevant bits. But yeah, the fundamental answer is like, there are hundreds of papers published every day on arXiv. You ain't going to read that.
That's true of any.
Yeah, it's true fundamentally of any area right now. I wish I had something more positive to say. All right, well, if that's what we have, thank you so much for coming, and thank you so much for your questions. I really appreciate them.